Dried mud cracks at about 120 degrees. So does soap foam. So does cooling lava. None of them can count. None of them have met. And this keeps happening, a small set of numbers turning up in places with nothing in common, from your bloodstream to your city. That's either a message or something much less comforting. Let's get right into it. Number 9, the 120-degree rule. Let a mudflat bake in the sun, it splits. And where 3 cracks meet, they tend to meet at roughly 120 degrees. Soap foam does it. Cooling basalt does it. That's the Giant's Causeway in Northern Ireland, tens of thousands of stone columns packed together like a floor from another planet. The reason is almost insultingly simple. Picture a 3-way tug of war, everyone pulling equally hard. There's exactly one arrangement where nobody wins, evenly spaced 120 degrees apart. Surface tension, cooling stress, drying stress, all playing that same game, so they tend to stop in the same place. The rule isn't a rule, it's a stalemate. Repeat that stalemate across a surface and you get hexagons, which brings us to bees. In 1999, mathematician Thomas Hales proved that a hexagonal grid uses less total wall than any other way of tiling equal areas. Bees build the cheapest container on the menu, except they might not be building it. In 2013, engineers at Cardiff University argued the cells start out as circles and warm wax simply flows into hexagons by itself. Other researchers disagree, and that argument is still live. Either way, nobody picked the number. It's what's left after physics deletes the expensive options. Number 8, the number 23, and that's fine while nothing is moving. Start something flowing, and a second number shows up. Take speed, multiply by width, divide by how thick and sticky the fluid is. That's the Reynolds number. It has no units, no meters, no seconds, no kilograms, just a ratio. Under about 2,300, fluid in a pipe moves in neat parallel layers. Smooth, silent, boring. Push past that, and the flow breaks into eddies and goes turbulent. Roughly the same crossing point for water, air, or oil. Roughly the same whether the pipe is a drinking straw or an oil line. You've already watched this happen. Smoke lifts off a match in a clean ribbon for a few centimeters, then frays into curls. That fraying is the crossing live in front of you. Your blood normally stays under the line. Silent, layered, orderly. When a valve narrows or an artery stiffens, the speed climbs, the ratio crosses over, and the flow turns rough. Rough flow makes noise, which is roughly what a stethoscope is for. A heart murmur isn't a mysterious sound from a mysterious organ. It's a number that climbed too high inside a body built to stay under it. Your doctor is listening to your heart. What your doctor is measuring is a threshold. Number 7, the slope of disaster. Cross that line and you get chaos. The unsettling part is that chaos keeps books. Sort a year of earthquakes by size. For every quake near magnitude 6, you'll find roughly 10 near 5, around 100 near 4, about 1,000 near 3. Down a step, multiply by 10. Up a step, divide by 10. Geologists call this Gutenberg Richter, and that slope sits close to 1 in most places anyone has measured. Fine. Earthquakes are earthquakes, except a similar shape shows up in solar flares, in landslides, in wildfires, different materials, different timescales, one rough recipe for how often big beats small. Now the disturbing bit, and it isn't the math. If the giants follow the same rule as the small ones, then a monster probably isn't a special event with a special cause. It's an ordinary event that didn't stop. Rock slipped, failed to catch, and kept going, and the fault had no idea it was making history. That's also why nobody can tell you when. Seismologists can hand you solid odds across 30 years because the counting holds up. What they can't hand you is a warning, because so far, nothing reliably marks the beginning of a big one. The number tells you how often, it stays stubbornly quiet about when. Number 6, the 10% ceiling. Rock has no budget. It can slip for a meter or for hundreds of kilometers, and nothing stops it but geometry. Living things don't get that freedom, and the number that limits them is small. Sunlight gets captured by plants, then handed upward. Plant to grasshopper, grasshopper to frog, frog to snake. At every handoff, most of the energy disappears, burned as heat, spent on breathing and moving, dumped as waste. Only around 10% tends to reach the next level. Real ecosystems vary quite a bit, maybe at 5 to 20% depending on who's eating whom, but 10 is the working average. Picture a paycheck that loses 90% every time it changes hands. 10,000 becomes 1,000, becomes 100, becomes 10. 4 transfers in, there's nothing worth transferring. Which is why food chains are so short. Most run 3 to 5 links and then stop. Not because of danger, because the funding ran out. So there's no super predator that hunts lions. There's probably no 8-level food chain hiding anywhere. Whatever apex predator you can name is sitting at the last seat the math will pay for. Which is also why apex predators are rare, need enormous territory, and tend to vanish first when an ecosystem gets squeezed. Nature didn't decide against monsters, monsters got priced out. Number 5, the rank 1 rule. Energy explains ecosystems. It explains nothing about the sentence you're listening to right now. You're a UN, yet this sentence is obeying a number 2. Take a large pile of English text and rank the words by frequency. First place is the. Second place shows up roughly half as often. Third place, about a third as often. 10th place, about a tenth. Rank a word, and its frequency is roughly 1 divided by that rank. That's Zipf's law, named after the linguist who cataloged it in the 1930s and 40s. It shows up in English, in Mandarin, Russian, Arabic, Vietnamese. It's been found in languages nobody has fully translated. And it turns up outside language too. City populations, website traffic, surnames. Nobody voted on this. No committee assigned its share. You've never once thought about the frequency curve of your own vocabulary, and you're producing it anyway, live every time you open your mouth. Here's the awkward part. Linguists have argued for decades about whether the curve means anything at all. Because if you sit a monkey at a keyboard and let it hit random keys, including the space bar, the nonsense words it produces come out roughly Zipf-shaped too. So the pattern is real and nobody disputes it. What it proves is still being fought over, which is the first hint that some of these numbers might not be messages from the universe so much as things that are hard to avoid. Number 4, the exponent 1.15. Cities should be where this breaks down. Cities are planned, there are zoning boards, they hold meetings. In 2011, a team led by Louis Betancourt and Jeffrey West published an analysis in the Proceedings of the National Academy of Sciences. Cities they found scale on about 2 numbers: physical infrastructure, road surface, cable, gas stations, scales at roughly 0.85. Double the population and you need only about 85% more pipes and wires. Cities save exactly like bodies do. But wages, output, patents, new businesses scale at roughly 1.15, double the population, and output more than doubles. Each person becomes measurably more productive just by being surrounded by more people. That result has since been checked in American, European, Chinese, and Brazilian cities. Everyone loves that number. Now the invoice. Crime rates appear to scale superlinearly as well. So does the spread of some infectious disease, so do several stress-linked illnesses. The good list and the bad list ride approximately the same exponent, which suggests that urban energy and urban dysfunction aren't two forces fighting over a city's soul. They may be one process with 2 names. Keeping the patents while refusing the pathology looks difficult because both come from the same fact: more people colliding more often. Every city seems to be running the same trade. Nobody has found a better exchange rate. Number 3, the 3/4 law. Cities speed up as they grow. Living things do the opposite, and they do it on a number nobody has fully explained. In 1932, Swiss biologist Max Kleiber measured how much energy animals burn at rest and plotted it against body mass. The obvious prediction was 1-to-1. Twice the animal, twice the fuel. That didn't fit. The next prediction, based on surface area, was 2/3. That didn't fit either. What fit was 3/4. Compare an elephant to a mouse. The elephant is around 200,000 times heavier, but burns something like 10,000 times more energy, gram for gram. Elephant tissue idles far slower than mouse tissue. Same chemistry, completely different speed. The leading explanation from West, Brown, and Inquist in the late 90s is that big organisms are built around branching delivery networks, arteries into capillaries, trunk into leaves, and filling a 3-dimensional body with that kind of network tends to produce quarter power exponents. It's elegant. It's also still argued about. Plenty of biologists think the exponent drifts between groups and that no single number covers everything. The drift doesn't save you though, because everything downstream comes in quarters too. Heart rate scales at roughly -1/4. Bigger animal, slower pulse. Lifespan scales at roughly +1/4. Bigger animal, longer life. 2 numbers, same strength, pointing in opposite directions. Multiply them together and something uncomfortable falls out. Number 2, 1 billion beats. Slower pulse, longer life. Multiply a quarter power slowdown by a quarter power extension, and the exponents cancel. Total heartbeats in a lifetime comes out roughly constant. Cardiologist Herbert Levine laid this out in the Journal of the American College of Cardiology in 1997, and the numbers are hard to look away from. A pygmy shrew runs at over 1,000 beats a minute and is gone in about a year and a half. An elephant idles near 30 and lives for decades. Both land somewhere near 1 billion beats. Cats, rabbits, horses cluster too. Actual measurements scatter somewhere between roughly 700 million and 1.5 billion. So this is a strong pattern, not a law of physics. Across a size range of 100,000 to 1, that scatter is remarkably small. Before anyone panics, this does not mean exercise spends your allowance faster. It seems to run the other way. Trained hearts rest slower, and a lower resting heart rate tends to track with a longer life, not a shorter one. You can't bank beats by sitting still. And here's the twist. Humans sit off the curve. We get somewhere around 2 to 3 billion, roughly double what our body size predicts. That's not a superior heart. It's plumbing, vaccines, antibiotics, refrigeration, and surgery. Other primates run high as well, so part of the head start was already ours, but most of it we built. Every mammal seems to get issued about the same allotment. We're the ones who filed a complaint and got a second one. Number 1, the number that isn't there. Which brings us to the most famous number in nature. 1.618, the golden ratio, phi. The one on the posters, in the design tutorials tattooed on forearms, supposedly hidden inside seashells, galaxies, cathedrals, and your own face. Very little of that survives measurement. The Nautilus shell is the flagship example, and it goes first. In 1999, mathematician Clement Falbo measured chambered Nautilus shells at the California Academy of Sciences and got ratios from about 1.24 to 1.43, averaging around 1.33. Later, Christopher Bartlett measured 80 shells in the Smithsonian collection and averaged about 1.31. The shell is a genuinely beautiful logarithmic spiral. It just isn't that one. The Parthenon works only if you choose the right corners to measure from. The Mona Lisa claim depends on where you decide the rectangle stops. George Markowski went through the catalog in 1992 in a paper for the College Mathematics Journal and kept finding the same failure. The number appears once a human picks the endpoints. One case does hold up. Seeds and leaves really are arranged near 137.5 degrees, but not for beauty. That angle survives because it's the least cooperative angle available. Nothing ever lines up, so nothing ever overlaps. It's a packing constraint, not a work of art. And that's the whole video, sitting right there. Every number that held up tonight was a constraint. The cheapest angle, the threshold, the slope, the ceiling, the exponent, the allotment. None of them decorative, none of them chosen. The universe probably isn't writing numbers into things, it's running out of options. We're the ones who show up afterward with a ruler, find the leftovers, and call it a design. That's all for today. I'll be making similar videos in the future. Subscribe to see them. End.